We will never leave the Milky Way, not in 1,000 years, not in 1,000,000, not ever. And the reason has nothing to do with lack of ambition, funding, or imagination. The barrier is written into the structure of space-time itself, into the chemistry of living cells, into the way energy scales with velocity, and into the unforgiving arithmetic of cosmic distance. Most people assume this is a problem we'll solve eventually, the way we solved flight or computing. But some problems don't have solutions. They have limits. And those limits, when you stack them together, don't leave room for exceptions. Here's the first number that matters. The Andromeda Galaxy, our nearest large galactic neighbor, sits roughly 2.5 million light-years away. That distance alone sounds abstract until you convert it into something measurable. Light, moving at exactly 299,792,458 meters per second, takes 2.5 million years to cross that gap. A photon that left Andromeda when early hominids were just beginning to use stone tools is only now entering our telescopes. And Andromeda is close. Most galaxies we can observe are billions of light-years away. The edge of the observable universe sits about 46 billion light-years out, and everything beyond that is not just far, it's causally disconnected from us. We will never see it, never reach it, never interact with it in any way. But let's set aside the rest of the universe and focus only on the Milky Way's immediate surroundings. Even here, in what we might call our local neighborhood, the distances are so extreme that the word distance starts to lose meaning. When people think about interstellar travel, they often picture it like a longer version of going to Mars. More fuel, more time, better engines, but fundamentally the same kind of problem. This intuition is completely wrong. The difference between interplanetary and intergalactic travel is not one of degree, it's one of kind. The gap between Earth and Mars averages about 225 million kilometers. The gap between the Milky Way and Andromeda is about 23 quintillion kilometers. That's 23 followed by 18 zeros. The human brain didn't evolve to process numbers like this. We treat them as placeholders, symbols on a page. But they represent physical reality, and physical reality enforces consequences. Let's start with speed. Suppose we built a spacecraft capable of traveling at 1% the speed of light. That's 2,997,924 kilometers per second, roughly 3,000 times faster than anything humanity has ever built. At that velocity, crossing the Atlantic Ocean would take about 1/100th of a second. Reaching Mars at closest approach would take roughly 4 minutes. It would feel, by human standards, instantaneous. Now apply that same speed to the distance between galaxies. At 1% of light speed, the journey to Andromeda would take 250 million years. The entire span of time since the first dinosaurs appeared on Earth is shorter than that. Every species of dinosaur, their entire reign, their extinction, the rise of mammals, the evolution of primates, the emergence of humans, the development of civilization, all of it fits comfortably inside the travel time of a 1% light speed journey to the nearest galaxy. And we haven't even built a spacecraft that can reach 1% of light speed. The fastest human-made object ever, the Parker Solar Probe, reaches about 0.064% the speed of light at its peak velocity. And it achieves that only by falling toward the Sun and using gravitational assists. Sustaining that speed across interstellar space, let alone accelerating further, is not a matter of better engineering. It's a matter of energy. Energy scales with the square of velocity. If you want to double your speed, you need 4 times the energy. Triple the speed, 9 times the energy. This relationship is not a limitation of current engines. It's a consequence of kinetic energy itself, baked into the equations that describe motion. To accelerate a 1-ton spacecraft to 1% the speed of light requires about 4.5 trillion joules of kinetic energy, assuming perfect efficiency. That's equivalent to the energy released by detonating more than a kiloton of TNT. And that's just the kinetic energy of the payload. In reality, you also have to accelerate the fuel, and the fuel to move the fuel, and the structure to contain it all. The tyranny of the rocket equation applies here. As your desired velocity increases, the mass ratio between fuel and payload grows exponentially. For chemical rockets, even reaching a tiny fraction of light speed is impossible, no matter how large the rocket. You run out of universe before you have enough fuel. Advanced propulsion concepts like ion drives or nuclear pulse propulsion can do better, but they all face the same wall. Energy requirements grow faster than our ability to supply them. But let's assume, for the sake of argument, that we solve the energy problem. Suppose we develop a propulsion system with near-perfect efficiency. perhaps using antimatter or some other energy-dense reaction. At 1% light speed, Andromeda is still 250 million years away. Let's push further. Suppose we reach 10% light speed. Now the journey takes 25 million years. Still longer than the entire history of recognizable human ancestors. What about 50% light speed? 5 million years. 90%? Just under 3 million years. Even at 99% the speed of light, the journey would take roughly 2.5 million years. And here we encounter the second wall, the one that doesn't yield to engineering at all. Biology. Human beings do not live for millions of years. Our cells accumulate damage. DNA degrades. Proteins misfold. Telomeres shorten. Metabolic byproducts accumulate. Radiation damages chromosomes. The mechanisms of aging are complex, but they all point in the same direction. Biological systems are not designed for indefinite operation. They are temporary structures, optimized for survival and reproduction over decades, not millennia. No known intervention has extended the maximum human lifespan beyond roughly 120 years. Some researchers believe that limit may be breakable with sufficient intervention, but even the most optimistic proposals don't suggest lifespans in the millions of years. They suggest hundreds, maybe a few thousand. Not enough. Not even close. So what about generational ships? A vessel large enough to support a self-sustaining population, traveling for millions of years while successive generations live and die on board. This idea sounds plausible until you examine what it actually requires. First, the ship must be large enough to maintain genetic diversity. A population of a few dozen people would collapse into inbreeding within generations. You'd need at minimum several hundred individuals, possibly thousands, to avoid genetic bottlenecks. Each person requires life support, food, water, air, waste processing, and living space. The mass of such a vessel would be enormous, which drives energy requirements even higher. But size is not the main problem. The main problem is time. Consider what happens to a closed system over millions of years. Every component degrades. Metal fatigues. Seals fail. Electronics suffer radiation damage. Even if you design for redundancy, replacement parts themselves degrade while in storage. Cosmic rays, which permeate interstellar space, gradually damage everything they pass through. Shielding helps, but perfect shielding is impossible. High-energy particles will always penetrate. Over short timescales, this is manageable. Over millions of years, it becomes cumulative and catastrophic. You would need not just spare parts, but the ability to manufacture spare parts from raw materials, which means carrying entire industrial facilities. You would need to maintain not just the knowledge of how to operate and repair every system, but the social and educational infrastructure to transmit that knowledge across tens of thousands of generations. Human civilizations on Earth, with all the resources of a planet, have never maintained continuity over such timescales. Languages change. Knowledge is lost. Cultures transform. The people who arrive, if anyone arrives, would be so far removed from the people who departed that they might not even remember why the journey began. And that assumes the journey goes well. Any catastrophic failure, a reactor breach, a collision with interstellar debris, a failure in the life support system, ends the mission. There are no rescue missions. No one is coming. The ship is alone in the space between galaxies, millions of years from help, surrounded by vacuum and radiation. The probability of mission success over such timescales approaches zero. But let's set aside generational ships and consider another idea. What if we don't send living humans? What if we send frozen embryos, or digital minds, or something else that doesn't require continuous life support? This seems more feasible, but it only shifts the problem. Frozen biological material still degrades over time, even at cryogenic temperatures. Background radiation still damages DNA. Storage systems still fail. And even if you could perfectly preserve embryos for millions of years, who raises them on arrival? You'd need either robots sophisticated enough to nurture human children, which introduces its own set of unsolvable problems, or you need a destination with a pre-existing infrastructure, which obviously doesn't exist. Digital minds face different problems, but no fewer of them. Data storage degrades. Cosmic rays flip bits. Error correction helps, but over millions of years, even tiny error rates compound into data loss. And a digital mind that arrives after millions of years of isolation, with no interaction, no sensory input, no update or change, might not be recognizable as a mind anymore. Every alternative, every clever solution, runs into the same fundamental issue. The timescale is too long. Millions of years is not a duration human systems, biological or technological, are built to endure. We design things for decades, maybe centuries if we're optimistic. Asking them to function for millions of years is not a matter of building them better. It's asking them to do something they are not, in principle, designed to do. Now let's examine special relativity, because this is where people often think they've found a loophole. Time dilation. If you accelerate to a speed close to the speed of light, time for you, aboard the spacecraft, slows down relative to the rest of the universe. At 99.9% the speed of light, time aboard the ship passes roughly 22 times slower than time outside. A journey that takes 2.5 million years in the external reference frame might feel like only about 100,000 years to the travelers. Push closer to light speed, and the effect becomes more extreme. At 99.99%, the factor increases to about 223. At 99.999%, about 7,000. In principle, if you could accelerate arbitrarily close to the speed of light, you could cross any distance in what feels, to you, like a manageable duration. This sounds like a solution until you look at what it costs. Accelerating to these speeds requires energy that grows not linearly, but exponentially as you approach light speed. The relativistic kinetic energy of an object is given by the Lorentz factor, which approaches infinity as velocity approaches the speed of light. To accelerate a single kilogram of mass to 99.99% of light speed requires more energy than the total annual energy consumption of human civilization. And you don't send 1 kilogram. You send a ship. With fuel. With shielding. With life support. The energy requirement becomes astronomical in the literal sense. There is no plausible source of that much energy. Antimatter reactions, the most energy-dense process we know, convert mass to energy with perfect efficiency according to Einstein's equation, E equals mc squared. But even if you could somehow gather and store enough antimatter, the mass you'd need to carry as fuel would itself require energy to accelerate. You end up in a recursive problem. The faster you want to go, the more fuel you need. The more fuel you carry, the more energy you need to accelerate it. At relativistic speeds, this spiral becomes unmanageable. And even if you solve the energy problem, time dilation doesn't help the people left behind. To travelers moving at near light speed, the journey to Andromeda might subjectively take a few years. But in the rest frame of the Milky Way, millions of years still pass. Everyone they knew is dead. The civilization that sent them is gone. The languages they spoke are extinct. The species they belonged to may have evolved into something unrecognizable, or gone extinct entirely. They arrive in a future that has no connection to their past. They are, in every sense that matters, isolated. And they can never return, because the return journey would cost the same energy and take the same time. From the perspective of the galaxy they left, they might as well have vanished. There's another issue with near-light speed travel that's rarely discussed. Interstellar space is not empty. It contains hydrogen atoms, roughly 1 per cubic centimeter on average, along with trace amounts of helium and dust grains. At low speeds, these particles are harmless. At 99% the speed of light, each hydrogen atom you collide with carries kinetic energy equivalent to a particle in a high-energy accelerator. These collisions produce radiation. Lots of it. The faster you go, the more intense the radiation becomes. At extreme relativistic speeds, the diffuse hydrogen in front of your spacecraft effectively becomes a forward-facing beam of deadly radiation. Shielding helps, but it adds mass, which requires more energy to accelerate, and no amount of shielding can completely block high-energy particles. Travelers aboard such a ship would be exposed to radiation doses that accumulate over the journey. Even if the subjective journey time is short, the radiation exposure is determined by the distance traveled and the speed, both of which remain enormous. This is not a minor engineering problem. It's a fundamental constraint imposed by the structure of matter and the nature of high-energy collisions. Let's talk about deceleration, because people often forget that getting somewhere is only half the problem. If you accelerate to near light speed, you also have to slow down, unless you plan to shoot past your destination at relativistic velocity and keep going forever. Deceleration requires the same amount of energy as acceleration. That means you need to carry twice as much fuel, or find some way to decelerate without fuel, perhaps using a magnetic sail to drag against the interstellar medium. But that process is slow and only works if the destination has a magnetic field or charged particle environment to push against. Andromeda's intergalactic space does not provide that. You're on your own. The fuel cost of a round trip, accelerating and decelerating twice, becomes so prohibitive that even theoretical propulsion systems struggle to justify it. Now consider what happens if we ignore all these problems and imagine, purely hypothetically, that a probe or ship somehow makes it to Andromeda. What then? The goal of exploration is to learn, to observe, to send information back. But information can't travel faster than light. A radio signal sent from Andromeda back to the Milky Way takes 2.5 million years to arrive. If the probe reaches Andromeda 5 million years after launch, the report it sends back arrives 7.5 million years after the mission began. Humanity, if it still exists, will have changed beyond recognition. The stars will have moved. Civilizations will have risen and fallen countless times. The information, when it finally arrives, will be a message from the deep past, transmitted by a mission no one remembers, sent by a species that may no longer exist. The causal loop between action and result is so stretched that it ceases to function. Exploration requires feedback. It requires learning and adapting. When the feedback loop takes millions of years, exploration becomes meaningless. There's also the question of why. Why would a civilization invest the resources necessary to attempt intergalactic travel? The most common answer is survival. If the Milky Way becomes uninhabitable, perhaps due to a nearby supernova, a gamma ray burst, or the eventual collision with Andromeda in about 4.5 billion years, humanity might need to leave. But this logic collapses under scrutiny. If the threat is localized, moving within the galaxy makes far more sense than leaving it. The Milky Way contains hundreds of billions of stars. If one region becomes dangerous, others remain safe. The energy cost of traveling a few hundred light years to another star system is incomparably smaller than the cost of intergalactic travel. And if the threat is galaxy-wide, something catastrophic enough to render the entire Milky Way uninhabitable, then the same threat likely affects nearby galaxies as well. Andromeda is not far enough away to escape a cosmic-scale disaster. The only scenario where intergalactic travel makes sense is one where the Milky Way is uniquely doomed and everywhere else is fine. No such scenario exists in known physics. Let's consider the Milky Way-Andromeda collision specifically, since people often cite it as a reason we need to leave. In about 4.5 billion years, the two galaxies will merge. This sounds violent, but galactic collisions are not like car crashes. Galaxies are mostly empty space. Stars are so far apart that even when two galaxies interpenetrate, the probability of any two stars actually colliding is negligibly small. What happens instead is gravitational reshuffling. Orbits change. Some stars are flung out into intergalactic space. Others fall toward the merged core. Gas clouds collide and trigger bursts of star formation. From the perspective of any individual star system, the merger is a slow, almost imperceptible process. The Sun, if it still exists, will likely survive the merger intact, though its orbit will change. Life on Earth, if any remains, faces far more immediate threats, such as the Sun's gradual brightening, which will render Earth uninhabitable in about 1 billion years, long before the collision. The collision itself is not a reason to leave the galaxy. And even if it were, 4.5 billion years is enough time to move to a safer orbit within the galaxy, not leave entirely. We also need to address the idea that future technology will somehow solve these problems. This is a common refrain. We didn't think we could fly, and then we did. We didn't think we could split the atom, and then we did. Surely, given enough time, we'll find a way to leave the galaxy. But this reasoning conflates two different kinds of problems. Flight and nuclear fission were engineering challenges constrained by human ignorance, not by the laws of physics. Once we understood aerodynamics and nuclear reactions, building planes and reactors was difficult but possible. Intergalactic travel is not constrained by ignorance. It's constrained by physics itself. The speed of light is not a technological limit. It's a property of space-time. Energy requirements are not estimates. They're consequences of relativity. Biological lifespan is not a design flaw. It's an outcome of thermodynamics and chemistry. These limits don't go away when you learn more. They become clearer. People sometimes invoke concepts like warp drives or wormholes as potential solutions, but these are not technologies. They are speculative ideas based on manipulating spacetime in ways that require exotic matter with negative energy density, something that has never been observed and may not exist. Even if it does exist, the amounts required to create a traversable wormhole or a warp bubble are so large that they exceed the mass energy of entire stars. And even if you could create such structures, they introduce causality violations, allowing for time travel and all the paradoxes that come with it. General relativity permits these solutions mathematically, but that doesn't mean they're physically realizable. Mathematics allows for many things that nature does not. A theory that permits contradictions is not a useful theory. Warp drives and wormholes remain, at best, mathematical curiosities. At worst, they're impossible. Betting the future of intergalactic travel on them is like betting on magic. Another idea people propose is generation ships that self-replicate, sending out new ships at each stop to spread across the universe. This doesn't solve the intergalactic problem. It just delays it. Each new generation of ships still faces the same energy and time constraints. And self-replication introduces new challenges. A system capable of autonomously building copies of itself from raw materials is far more complex than a simple probe. It needs mining equipment, refining facilities, manufacturing plants, quality control, all operating without human oversight for millions of years. The failure rate of such a system, compounded over many generations, approaches certainty. And even if it works, spreading within the galaxy is one thing. Crossing intergalactic voids is another. The gaps are too large. The energy cost too high. The timescales too long. Some people suggest we could send information instead of matter. Transmit the human genome, or uploaded minds, or detailed construction plans, and let some distant intelligence rebuild us. But this assumes a recipient. Andromeda has no one to receive the message. As far as we know, there is no other intelligent life there, no infrastructure, no welcoming committee. You'd be sending a message into the void, hoping someone, someday, finds it and decides to reconstruct whatever you encoded. And even if they did, what arrives is not you. It's a copy, built from a blueprint, with no continuity of experience. Philosophically, this raises questions about identity and continuity, but practically it's also useless for the goal of leaving the galaxy. You, the sender, are still here. You haven't left. You've just sent information outward, and information that might never be received or understood. Let's also consider the resources required for any intergalactic mission. Humanity currently uses about 580 million terajoules of energy per year. The energy required to send even a small probe to Andromeda at a meaningful fraction of light speed exceeds global annual energy consumption by orders of magnitude. Where does that energy come from? Solar panels? They need to cover areas larger than planets. Nuclear reactors? You'd need thousands of them running continuously for decades just to charge the fuel. Fusion? Even if we achieve practical fusion, the energy density is still insufficient for relativistic travel. Antimatter? We produce antimatter and particle accelerators at rates measured in nanograms per year. Scaling that up to kilograms, let alone tons, would require energy inputs that dwarf current global capacity. Every proposed solution leads back to the same bottleneck: energy. And energy is not the only resource. You also need materials. A spacecraft capable of surviving the journey needs shielding, structure, propulsion, life support, navigation, communication, power generation, and redundancy in all systems. Each component requires manufacturing, testing, and quality assurance. The supply chain for such a mission would span the entire industrial capacity of human civilization. And for what? To send something we'll never hear from, to a place we can't reach, for reasons that don't justify the cost. The rational allocation of resources does not support intergalactic exploration. It supports incremental expansion within the galaxy, where the returns are measurable and the feedback loops functional. There's a deeper issue here that people rarely articulate. The assumption that expansion is always possible, always desirable, is a bias rooted in human history. For most of our existence, there was always more land over the horizon, more resources to exploit, more frontiers to cross. But the universe is not infinite in the ways that matter. It's bounded by the speed of light, by the availability of energy, by the decay of matter, by the limits of biology. These boundaries are not temporary. They are structural. Accepting them is not pessimism. It's realism. The Milky Way itself is enormous. It contains between 200 and 400 billion stars, depending on the estimate. Many of those stars have planets. Some of those planets likely have conditions suitable for life. If humanity survives and expands, there is more than enough room within this galaxy to sustain growth for timescales longer than the current age of the universe. The problem is not a lack of space. The problem is a psychological expectation that growth must be unlimited. But unlimited growth in a finite system is a contradiction. At some point, every expanding system encounters limits. For humanity, the limit of expansion is the edge of the Milky Way. Not because we lack ambition, but because the universe itself says no. Consider the trajectory of human exploration. For most of history, we explored by foot, then by boat, then by vehicle, then by aircraft, then by spacecraft. Each transition required more energy and more technology, but each was feasible because the distances involved scaled with our capabilities. The jump from ocean travel to space travel was enormous, but it was still possible because the Moon and Mars are close enough, in cosmic terms, that chemical rockets can reach them. The jump from interplanetary to interstellar travel is vastly larger, but still conceivable with advanced propulsion over timescales of centuries. The jump from interstellar to intergalactic is not the next step on that ladder. It's a different category entirely. It's the difference between difficult and impossible. Impossible is a strong word, and people resist it. We want to believe that sufficient ingenuity can overcome anything. But impossibility is not a failure of imagination. It's a feature of reality. You cannot build a perpetual motion machine because thermodynamics forbids it. You cannot transmit information faster than light because causality forbids it. You cannot leave the galaxy because distance, energy, time, and biology all forbid it, not individually, but together, in a way that leaves no room for exceptions. There's one more constraint worth mentioning, one that's rarely discussed because it operates on timescales even longer than the ones we've been considering. The universe is expanding. The space between galaxies is growing, driven by dark energy, a component of the cosmos that acts as a kind of repulsive force on large scales. Andromeda is currently moving toward the Milky Way due to local gravitational attraction, but most galaxies are moving away from us, and that recession is accelerating. Billions of years from now, galaxies outside our local group will be so far away, and receding so fast, that light from them will never reach us. They will disappear beyond the cosmic horizon, causally disconnected forever. Even if we could somehow travel at the speed of light, there are galaxies we could never reach because the space between us and them is expanding faster than we could cross it. This is not a problem we'll face soon, but it illustrates a point. The universe has built-in horizons. Some places are fundamentally inaccessible, not because we're too slow, but because the structure of space-time makes them unreachable. Returning to Andromeda, the closest large galaxy, let's consolidate what we know. It's 2.5 million light-years away. To reach it in less than a few million years requires traveling at a significant fraction of the speed of light, which requires energy we cannot generate. Even if we could generate that energy, accelerating to such speeds exposes travelers to lethal radiation and requires deceleration energy we cannot carry. Even if we solved propulsion, human biology cannot survive journeys lasting millions of years, and generational ships face compounding failure rates that make success implausible. Even if we sent probes instead of people, the communication delay makes the mission pointless. Even if we ignored all practical concerns and sent something anyway, the resource cost would exceed the capacity of human civilization with no proportional benefit. Every angle leads to the same conclusion. Intergalactic travel is not a problem to be solved. It is a boundary to be acknowledged. This does not mean humanity's future is small. The Milky Way offers more stars, more planets, more possibilities than we could explore in the remaining lifespan of the universe. If we survive and expand, we will have access to resources and environments beyond anything our ancestors could have imagined. But that expansion has limits. Those limits are not arbitrary. They are set by the same physical laws that allow stars to shine and planets to form. Respecting those limits is not a retreat from ambition. It's an acceptance of reality. Understanding space often means understanding limits, not ambitions. The distances are too great. The energy requirements too high. The timescales too long. The biological constraints too firm. The universe is not a place designed for easy travel. It's a structure governed by rules that operate without regard for what we wish were true. We can push against those rules, and we have, achieving things our ancestors would have called miraculous. But some rules do not bend. The edge of the galaxy is one of them. We will never leave the Milky Way. Not because we lack the will, but because the universe does not permit it. And that's not a tragedy. It's simply the way things are. If this kind of careful, evidence-based exploration of what space actually allows resonates with you, consider subscribing. There's more to examine, more limits to understand, more quiet truths to uncover. The algorithm will keep suggesting whatever you engage with, so if thoughtful analysis is what you prefer, it helps to signal that. Not a demand. Just an option. Either way, thank you for thinking through this with me.